Cool. Well, morning everybody. My name is Steven. I'm a data scientist at Shopify. And today I want to talk about a project my team has worked on for a greater part of the past year around preventing credit risk in our payments product. And throughout this talk, I want to talk about the experience of how we went through a 0 to 1 project of setting up a machine learning model in a space where there really wasn't one, and some of the main takeaways we learned along the way. So just introducing myself again, I'm currently at Shopify working on measuring and combating different risks that we face in our financial products. Before that, I have good 7 years experience in consumer finance, working on a good mix of data science problems there. I studied math in school, like maybe some of you did. Decided I wanted a really hands-on job where I could see the fruits of my labor in action, and that's how I ended up in data science. So to explain Shopify, we're an e-commerce platform company. What that actually means, the way I like to communicate that to people is Shopify doesn't sell you goods, but we provide platforms and services to a lot of the merchants that do. If you look at Shopify by the numbers, we've got 2 million merchants in 175 countries, so pretty big global footprint. In terms of buyers, over 600 million people shopped at a Shopify store online last year. A lot of them probably didn't even know it was a Shopify store. And we process $85 billion of payments through Shopify Payments. And Shopify Payments is the product that this project is actually working on. So I want to take the time to explain what Shopify Payments is. So put simply, Shopify Payments is a way to let merchants handle and process payments. And what we do on the back end is we provide a lot of the infrastructure and act as an intermediary between the buyer, the merchants, the banks, and everything we do is to make that process seamless for all parties involved. So with something like payments, this is a very fundamental thing for an online store. So all payments involve risk. Unfortunately, there's no such thing as a risk-free payment yet. And payments are a contract between a buyer and a merchant. And those contracts can fail for a number of reasons, whether it's fraud, like the buyer's payment information is compromised. It can be human error. It can be technical error. A lot of different reasons that this contract can fail. So for a company the size of Shopify, doing tens of billions of dollars of payments a year, even small risk can have pretty significant financial impacts. Now, the specific risk we're focused on for this project is something called credit risk. And to explain this in a scenario, this typically happens when you have cases where a lot of buyers to a given shop are unhappy with their product and they're looking to make returns, and the merchant gets hit with such a volume of refunds and disputes and chargebacks that they don't actually have the money to cover those costs. And due to kind of the inner workings of this, Shopify ends up on the hook for these losses. Now, to get into a little bit of the technical mechanics of this, because it matters for some of the modeling steps, all shops have something called a payments balance. You can think of that as sort of like a checking account where you get inflows and you get outflows. So your standard operating shop is going to have rises and falls to this balance as as they make sales, as they make payouts. And then you can see through this hypothetical example of kind of how a loss happens, where just too many chargebacks and refunds add up, the balance goes negative for an extended period of time, and at that point, it's considered a loss. So to make this a little more real, I'll go through a hypothetical example of kind of how this mechanic works. So we have a shop that sells shoes. They're an established merchant. They've been doing consistent sales for a while, and everything's going fine, but suddenly they get hit with supply chain issues, and they can't get their shoes from their upstream supplier. So buyers aren't able to get their shoes, and they're unhappy, understandably, because they already paid for their shoes. So they're going to the merchant trying to get refunds, or they're getting the bank involved for a dispute if the merchant isn't able to help them. Unfortunately, the merchant has other costs, and they paid out their balance to cover those costs. We've got a bit of a problem now where a lot of buyers paid for their shoes, but they're not getting their shoes because the merchant can't get it from their supplier. The merchant also can't refund the buyers even though they'd like to because they just don't have the funds. And what happens in this case is Shopify will step in and make good with the buyer and cover that money while we wait for the merchant to kind of solve their issues or re-raise cash again. And so this is the problem we're trying to get ahead of. And this was just one example, the supply chain issue, where from a modeling perspective, we could have figured this out maybe by noticing when fulfillments dropped off or inventory wasn't increasing at the normal rate. There's a couple other drivers like fraud or if a business is just failing financially. There's a pretty good variety of root causes here that we need to cover in our feature space. So after the rapid growth of payments through the years leading up to the point where we're doing tens of billions of dollars of payments, I think as a company, we really realized we needed to improve our risk detection and risk prevention capabilities here. So before I actually get into the modeling part, I'll explain how we actually protect against losses. Under the old way of doing things, there was no machine learning, no statistical modeling. Risky shop detection was based off of simple tripwires. So a simple rule set based on maybe one or two variables. And if a shop breached that variable, then they'd be flagged as high risk. These rules were often reactive and kind of lagged current trends by a matter of months. And the rules just weren't that effective at actually figuring out which shops are high risk or not. So once a shop is flagged as high risk, they're placed under this manual process called risk review. So there's an actual team of people that's scouring over the shop details. And depending on their review, they'll do a couple of things. And the first order of defense here is educational assistance or guidance to help the merchant get off track. In a lot of cases with newer merchants, they might fall into some risky pitfalls that can lead to problems. In more severe cases, we can do things like temporarily pause payouts, hold a reserve on the account. And so where does machine learning fit into all this? Well, the goal with machine learning, in short, is much stronger detection of risky shops. And we want this risk detection to be ML-based. We want it to be based off a much more comprehensive set of risk signals. And we want the ability to retrain and update our model fairly often so that we're keeping up with the current trends, being proactive rather than reactive. So now we need to actually formulate a plan. We knew from the very beginning that in order to prevent losses, it wasn't enough to merely predict that a loss would happen. We had to really dig into the problem space and understand the scenarios, the triggers by which we would actually be able to step in and reduce our loss exposure. One of the first things we learned here is we need to detect a high-risk shop with enough time and enough leeway so that we actually have enough time to do something to prevent losses. And to give one example with some real features, it's typically good if we can detect a high-risk shop once like fulfillment starts slowing down or the inventory issues, but it's usually too late if a shop has a ton of buyers that are very angry and asking why they're not getting their goods. So kind of working through those different variables, we came to kind of a simplified, I'd say, set of scenarios we could look at for like advanced warning, medium warning, too late. And that was really helpful for us to understand, are we getting in front of high-risk shops with enough time to actually stem the losses? And this might seem obvious, but it's worth stating. Some shops have bigger losses than others. So there's a little bit of an exponential curve distribution here. And this matters for two reasons. One, because in our feature strategy, we need to make sure we're including features that give an estimate of like the scope or potential impact of losses. So telling like shops that could have a really big loss versus a really small loss. And then when it comes to the modeling, I'll explain this a little more later, but we also need to account for this in our model training and sampling strategies. And I mentioned there were a couple different drivers of losses. We learned some of these are much more recoverable than others. So in the case of fraud, that's typically less recoverable because the merchant on the other side of this is actually trying to commit fraud. Whereas like in the cases with newer merchants, if we help them avoid a common pitfall, then we typically have much more leverage there to prevent losses. So we have kind of a better shaped problem statement now, where we're going to prevent payments risk through early detection of high-risk shops on the most recoverable shops. So now getting into the modeling, I'd mentioned the concept of a payments account balance and how that worked as kind of a checkings account. And our first series of modeling was really motivated by the idea that if we could predict what a given shop's balance would be, then we could detect the cases where balance goes negative and we potentially have a loss. And so we started thinking about time series modeling and recurrent neural networks in particular. Won't go into too much detail on what RNNs are, but the idea was we could predict a time series of future payment balances by looking backwards at historical time series data of a shop's sales, their previous balance, features of that nature. So we had a couple problems with this approach. The first is that this target of the payments balance is actually really noisy when you consider all the ebbs and spikes of a merchant making sales or taking payouts. And this just, at the end of the day, even with smoothing, this wasn't the thing we were really trying to model. So we hypothesized and then actually saw in this sort of modeling setup, we would get credit for minimizing the error of predicting payments balance. But that didn't necessarily mean we were actually good at predicting losses. And then some of you know, neural net training is just hard. There's this really good blog post by Andre Karpathy where he talks about a lot of the reasons why neural net training is so difficult, because they can fail silently, they're a little bit hard to debug and reason about, and we faced a lot of these issues. We probably could have solved for a bunch of these issues, but given the time crunch we were under and the urgency of this project, we just didn't have time for that. How am I doing on time?
You good.
Cool. Then the last problem here is this was a really complex black box model. And while interpretability wasn't a hard requirement for this project, I still like having interpretability. I like being able to kind of pry the brains of my model, and I get comfort from knowing it's making smart correlations, and I can kind of build that intuition about how it's thinking. And we just weren't really able to get that with the RNN. So we took a lot of the learnings from our first iteration. We went back to the drawing board to come up with kind of a simplified second approach. And the first thing we dug in on was the target. So instead of a complex daily time series target trying to predict a balance vector of 90 days, we tried to distill this down to the most basic thing we care about, which in our case would be if a loss occurred or not. And we actually didn't just do that, excuse me. We also use what I call a leading indicator target, where the standard definition of a loss is if the balance is negative for 60 days, we ended up looking at like a leading target of if the balance is negative for 30 days. So there's a much higher target rate because there's more shops that hit 30 days versus 60 days. And we looked at this empirically that when you consider the trade-off between higher target rate and kind of, how do I put this, not immediately going after the thing, after the risk dimension we're trying to capture, we found that empirically this still worked pretty well, and this was a smart trade-off for us. And then I mentioned we had some imbalance issues where not only are shops with losses relatively rare, but the distribution of dollar losses there follows that exponential distribution. So we solved this two ways, where first we did a stratified sampling approach to our training sample, where we just made sure shops with losses were better represented. And then in terms of how we accounted for the higher dollar amount, what we ended up doing was weighting the model training by some variable that kind of proxied for exposure. This was something we did at kind of a quick clip, so if we had more time, I might have investigated like an explicit regression on this, but nonetheless. And then one of the last updates we did that was really helpful, with the RNN, we had been using as features full daily vectors of a bunch of different variables like sales going 90, 120 days back. And that was a little bit difficult because it blew up the dimensionality of our feature space. And it took a lot of sample just to get the RNN to really kind of learn that higher dimensionality feature space. And what we found is we could simplify this data with just simple aggregations, like averages, min, max, slopes. And we found that we're able to reduce the feature set dimensionality by a really long ways, get dense features, and we really weren't losing that much of the critical information in these features. So this was another place where we simplified, and we ended up trading off a ton of complexity for only negligible modeling performance. So with all that said, we've got a final model. Just to talk over the specs of the model really quickly, we used an XGBoost classifier for this with the different weighting strategies I talked about. It was a couple thousand trees and about 50 features. And with the current size of our training sample, we can train this on a medium-sized distributed cluster, and it only takes about an hour or so. So we've got a little bit of gas in the tank when it comes to increasing the sample size here. And as I start, excuse me, as I start to wrap up, I just want to hit on what we actually accomplished here. So the first, of course, is that we significantly improved risk detection. I can't get into the specific numbers, unfortunately, per our legal team, but I'm pretty happy with the numbers that we got. And not only that, but through a lot of our scoping out the problem space, we came to a more consistent framework and terminology when it came to thinking about losses and loss prevention. And this was super helpful just so that as we're talking with our non-data stakeholders, we're all on the same page and using the same language. And I didn't get to go into our modeling infrastructure just for sake of time, but we also invested a lot upfront in getting good, robust training and inference pipelines off the ground. And that's the sort of thing that's going to pay dividends for us down the road, just being able to reap what we sowed there. So now I want to wrap up with just a couple of takeaways we learned through this project. And the first is just really thinking long and hard about what problem it is you're trying to solve. This wasn't a successful project because we did state-of-the-art research or we used a super complex algorithm. This was a successful project because we really dug into the data space, the problem space, and we learned what our model had to do to be successful, and then we just delivered on that. My second point is just being really judgmental about how you make trade-offs between speed to market and having the most performant model or the best solution. So this was a greenfield project, 0 to 1, as I mentioned. And that's really exciting for a data scientist because you have all these different great ideas running around in your head and you want to try all these different things. But ultimately, we had to be really disciplined about our time and how we invested it. And we had to really make sure we were focused on the essentials first. And then the last point is just, as you're going through the project, keep an eye on not just what you're doing for the current iteration, but how can you make future iterations of this successful? So one example I mentioned was the training pipeline work we did. We did a lot of upfront work that is going to pay off a lot when we're thinking about versions 2, 3, et cetera, down the road. And if you're going through a project like this and you just get ideas that you don't have the time to address now, whether that's a really good like feature data source or an interesting modeling algorithm, something like that, just keep a tracker, write it down, and you'll have a great list of ideas to go off of once you start thinking about how you keep solving this problem down the road. That covers it. Q&A.